Identifying handwritten digits with logistic regression in PyTorch. Introduction to deep learning for digit recognition. Why digit recognition matters in the real world. How PyTorch and logistic regression help solve this problem. What you will learn step by step. Running the cell now. About the dataset. We use the digits dataset from scikit-learn. It contains 8 by 8 images of handwritten digits 0 through 9. Each image is labeled with the correct digit. This is a simple version of the classic NIST problem. Great for learning and quick experiments. Running the cell now. We want to keep our output clean and easy to follow. Suppressing warnings in notebooks can help you focus on results. Always suppress warnings for cleaner output. Import warnings, warnings.filter warnings, ignore. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. This code snippet sets the stage by importing necessary libraries and suppressing warnings for cleaner output. The fixed random seed ensures reproducibility throughout the lesson, so any random operations on the digits dataset produce consistent results. This foundational step is essential before we begin exploring and modeling the handwritten digit images. This step hides unnecessary warning messages, so nothing distracts you during learning. Let us load our handwritten digits dataset. This is included in scikit-learn and does not require downloads. Data setup. From scikit-learn.datasets import load_digits. Digits equals load_digits. Y equals digits.data, digits.target. Print x.shape. Print y.shape. Running the cell now. Here, we see the shapes of our feature matrix X and label vector Y from the digits dataset. X has 1,797 samples, each with 64 features corresponding to the 8 by 8 pixel values, and Y contains 1797 labels, one for each image. This confirms that our data and labels are aligned, ready for further processing in our digit recognition task. You now have a feature matrix X and a label vector Y. There are 1,797 images in total. Each image is flattened into 64 features, because 8 by 8 equals 64 pixels. Let us visualize the very first handwritten digit from the dataset. It helps to see what kind of data we actually use. Let us print and view the first image. Import matplotlib.pyplot as plt. plt.gray. plt.matshow, digits.images, 0. plt.title, true label, digits.target, 0. plt.show. Running the cell now. Here, we visualize the very first image in the digits dataset, which is an 8 by 8 grayscale image of a handwritten digit. The title shows the true label, helping us connect the pixel pattern we see to the actual digit it represents. This step is crucial for understanding the raw input data before moving on to pre-processing or model training. This shows the image as humans and computers see it. The title displays the actual label for this digit. Visualization makes the problem less abstract and more relatable. What is logistic regression? A simple classification algorithm for dividing data. Works by estimating class probabilities. For digits, it predicts which number best fits the input image. Despite its name, logistic regression is used for classification. Running the cell now. It is important to know how many examples of each digit we have. This prevents bias and helps us notice data quality issues. Let us check the distribution of digit labels. Import pandas as PD. Import seaborn as SNS. SNS.set_style, white grid. df_labels equals PD data frame, label, Y. SNS.countplot, X equals a label, data equals df_labels, palette equals viridis. plt.title, number of samples per digit. plt.show. Running the cell now. This count plot shows the distribution of digit labels in our dataset, highlighting how many samples we have for each digit from 0 to 9. Notice any class imbalances, as they can affect how well the logistic regression model learns to classify each digit. This step connects to our lesson by preparing us to understand the data our classifier will work on. This bar chart gives a clear picture of how our digit samples are balanced. Equal distribution is good for training fair models. Machine learning works best when we split data for training and testing. Normalization makes features similar in scale, which helps neural networks learn. Prepare data for PyTorch, train test split and normalization. From sklearn.model_selection import train_test_split. From sklearn.preprocessing import standard scalar. x_train, x_test, y_train, y_test equals train_test_split, x, y, test_size equals 0.2, random_state equals 42. Scalar equals standard scalar. x_train_scaled equals scalar.fit_transform, x_train. x_test_scaled equals scalar.transform, x_test. Print x_train_scaled.shape, x_test_scaled.shape. Running the cell now. This output shows the shapes of our training and testing datasets after splitting and normalization. Notice we have 1,437 samples for training and 360 for testing, each with 64 features representing the pixel values of the digit images. This confirms our data is properly prepared for logistic regression to learn and evaluate digit classification. We now have training and test sets with standardized features. Using random_state ensures our splits are predictable and repeatable. Introduction to PyTorch. PyTorch is a popular deep learning library. It makes building neural networks easy and flexible. We use tensors, which are special multidimensional arrays. PyTorch is especially strong for experiments and rapid ideas. Running the cell now. Torch models work best with their own data structures, called tensors. We wrap the data in Dataset and DataLoader helpers for easier batching. Batching means working with small groups of samples at a time, helping the training process. Convert data to Torch tensors and wrap in datasets. Import Torch. From torch.utils.data import tensor dataset, DataLoader. x_train_tensor equals torch.tensor, x_train_scaled, dtype equals torch.float32. x_test_tensor equals torch.tensor, x_test_scaled, dtype equals torch.float32. y_train_tensor equals torch.tensor, y_train, dtype equals torch.long. y_test_tensor equals torch.tensor, y_test, dtype equals torch.long. Train_dataset equals tensor dataset, x_train_tensor, y_train_tensor. Test_dataset equals tensor dataset, x_test_tensor, y_test_tensor. Train_loader equals DataLoader, train_dataset, batch_size equals 32, shuffle equals true. Test_loader equals DataLoader, test_dataset, batch_size equals 32. Running the cell now. This code converts our scaled training and test data into PyTorch tensors and packages them into tensor datasets, which group inputs and labels together. We then create DataLoaders to efficiently handle batch processing, here using batches of 32 samples, enabling easy iteration during model training and evaluation. Notice that no direct output is shown because these objects serve as essential building blocks for streamlined and flexible deep learning workflows in PyTorch. Your features and targets are now in Torch tensor form. We also created DataLoaders to easily feed mini batches during training and testing. PyTorch Logistic Regression Model Structure. One fully connected layer is enough for logistic regression. The input layer size matches our number of features, 64. The output layer has 10 units, 1 per digit class. We will not use any hidden layers for now. This shows how simple models can be powerful. Running the cell now. Here we define our logistic regression model using the PyTorch way. It has only one linear layer, which means weights are applied and outputs are produced directly. 10 outputs correspond to the 10 possible digits, 0 through 9. Define the logistic regression model in PyTorch. Import torch.nn as nn. Class logistic regression model, nn module. Def __init__ self. Super, logistic regression model, self, .__init__. Self.linear equals nn linear, 64, 10. Def forward, self, x. Outputs equals self.linear, x. Return outputs. Model equals logistic regression model. Running the cell now. This code defines a simple logistic regression model with one fully connected layer that maps 64 input features to 10 output classes, aligning with our digit classification task. Although there's no printed output here, the key takeaway is the model's architecture matches the lesson's intent, using a single linear layer for multi-class classification in PyTorch. This sets the foundation for training a straightforward classifier on our dataset. The class inherits from nn module, which is standard for all PyTorch models. Super just calls the base object to set up needed variables. We finish by creating an instance of the model ready to be trained. The loss function measures how far off our model's predictions are. Cross-entropy loss is the recommended choice for multi-class problems like digits. We use stochastic gradient descent as our optimizer. It helps our model learn by updating weights in small steps. Set up loss function and optimizer. Import torch.optim as optim. Criterion equals nn.crossentropy loss. Optimizer equals optim.sgd, model.parameters, lr equals 0.1. Running the cell now. This code block sets up the loss function and optimizer for training our logistic regression model, crucial steps before starting the training loop. We use cross-entropy loss to handle multi-class classification and SGD as our optimizer, which will update all model parameters, including the weights connecting the 64 input features to the 10 output classes. Although there's no printed output here, this setup ensures our model will learn to map input features to digit classes effectively. Setting a higher learning rate like 0.1 can speed up learning for simple models. We are now ready for actual model training. Training the model. We go through the data in batches for better memory use. On each batch, the model makes predictions and measures loss. We adjust the model's weights to reduce that loss. One full pass through the data is called an epoch. More epochs give the model more chances to improve. Running the cell now. Now we let our model learn from the data. Each epoch, we process all training images while tracking the loss. Printing every 5 epochs helps you watch progress without too much output. Run the training loop. Epochs equals 20. For epoch in range, epochs. Model.train. Total_loss equals 0. For batch_x, batch_y in train_loader. Optimizer.0_grad. Outputs equals model, batch_x. Loss equals criterion, outputs, batch_y. Loss.backward. Optimizer.step. Total_loss plus equals loss.item, asterisk batch_x.size, 0. Average_loss equals total_loss len, train_loader.dataset. If epoch plus 1%, 5 equals 0 or epoch equals 0. Print ft epoch plus 1, loss, average underscore loss, point for f. Running the cell now. This output shows the average training loss decreasing steadily over 20 epochs, highlighting how the model improves as it adjusts weights to better fit the data batch by batch. Notice the sharp drop by epoch 5, indicating significant learning early on, and the gradual smaller improvements afterward, reflecting fine-tuning. This confirms that running multiple epochs helps the model minimize error and better capture the underlying patterns in the dataset. Training reduces the average loss, meaning our model predictions become more correct. Watching loss fall is proof our logistic regression model is learning patterns in the digits. After training, we always want to test how well our model does on unseen data. Higher accuracy means our model is more reliable at identifying new handwritten digits. Evaluate test accuracy after training. Model.eval. Correct equals 0. Total equals 0. With torch.no_grad. For batch_x, batch_y in test_loader. Outputs equals model, batch_x. Underscore. Predicted equals torch.max, outputs, 1. Correct plus equals, predicted equals batch_y, .sum, .item. Total plus equals batch_y, .size, 0. Accuracy equals correct total * 100. Print, f test accuracy, accuracy a 0.2f%. Running the cell now. This output shows the final test accuracy of 97.22%, indicating how well the trained model generalizes to new, unseen data. After completing the training epochs, we switch to evaluation mode and use batches from the test set to measure performance without updating weights. Noticing a high accuracy here validates that the model's learn patterns during training effectively apply to real examples beyond the training batches. Accuracy tells you the % of images the model classified correctly. Even a simple logistic regression can reach high accuracy, showing how useful this approach is to start with. Let us see real results. Here, we randomly pick test images and show predictions alongside the true labels. This helps you connect actual images with what our model thinks. Show predictions for some test images. Import numpy as np. Examples equals np.random.choice, len, x_test_tensor, 8, replace equals false. Model.eval. With torch.no_grad. For idx in examples, img equals x_test_tensor, idx.numpy.reshape, 8, 8. Out equals model, x_test_tensor, idx.unsqueeze, 0. Pred equals out.argmax, dim equals 1, .item. plt.imshout.img, kmap equals a gray. plt.title, f predicted, pred, true, y_test, idx. plt.axis, off. plt.show. Running the cell now. This output shows a series of 8 test images alongside the model's predicted labels and the true labels, demonstrating how well the model generalizes to unseen data after training. Notice how each plot displays a grayscale 8x8 image with clear predictions, which helps us qualitatively assess the model's performance and spot any misclassifications. This connects directly to the goal of the training process, using batch data to iteratively improve the model's accuracy over epochs so it can correctly recognize new examples. Looking at predictions visually can give you confidence and a sense of how well the model learned handwriting patterns. A confusion matrix lets you see which digits the model confuses for each other. This is especially important for spotting weaknesses that pure accuracy cannot show. Look at a confusion matrix for test results. From sklern.metrics import confusion_matrix, confusion matrix display. Import matplotlib.pyplot as plt. All_preds equals. All_true equals. Model.eval. With torch.no_grad. For batch_x, batch_y in test_loader. Outputs equals model, batch underscore x. Underscore, predicted equals torch.max, outputs, 1. All underscore preds.extend, predicted.numpy. All underscore true.extend, batch underscore y.numpy. CM equals confusion underscore matrix, all underscore true, all underscore preds. Disp equals confusion matrix display, confusion underscore matrix equals CM, display underscore labels equals np.arrange, 10. Disp plot, cmap equals blues. plt.title, confusion matrix, test set. plt.show. Running the cell now. This confusion matrix summarizes the model's performance on the test set by showing how often each true digit was predicted as each class. Notice clusters along the diagonal, indicating correct predictions, and any off-diagonal values reveal common misclassifications. This visualization helps us understand the model's strengths and weaknesses after training through multiple epochs on batches. Each row shows the true digit, and each column shows what the model predicted. Dark squares on the diagonal are good because they show correct predictions. Try it yourself, predict your own digit image. Convert a simple 8x8 sketch of a digit into a NumPy array. Follow the same pre-processing and use the model for prediction. See how well the model handles new handwritten styles. Practicing with your own samples is a great way to learn. Post your results or questions in the YouTube comments below. Running the cell now. Here is a fun interactive example. You can enter your own 8x8 grid pixel values, like a mini drawing pad using numbers. The model will try to predict what digit you meant based just on those values. Hash optional, type a digit image as numbers for prediction. Import numpy as np. User underscore pixels equals. Print, enter 64 pixel values, 016, for an 8x8 image, separated by space. For I in range, 8. Row underscore values equals input, f row, I plus 1, 8, dot split. User underscore pixels dot extend, int x, for x in row underscore values. User underscore ing equals np dot array, user underscore pixels, dot reshape, 1, minus 1. User underscore img underscore scaled equals scalar dot transform, user underscore img. User underscore tensor equals torch dot tensor, user underscore img underscore scaled, dtype equals torch dot float 32. With torch dot no underscore grad. Output equals model, user underscore tensor. Predicted equals output.argmax, dim equals 1, dot item. Print, f predicted digit, predicted. Running the cell now. The output shows the predicted digit from based on your input of 64 pixel values representing an 8x8 image. Notice how the code reshapes and scales your numeric sketch before feeding it to the model, demonstrating how to pre-process your own handwritten samples for accurate prediction. This highlights the lesson's goal of practicing digit recognition using your custom-drawn inputs. Experiment and see if the model gets your digit right. You can also play with different patterns and see what it predicts. Where to go from here? Try increasing epochs to see how accuracy improves. Replace logistic regression with deeper layers for even better results. Try with the larger MNIST dataset next. Play with optimizers and learning rates. Share your experiments and subscribe for more tutorials. Running the cell now.